So now we come to some properties of glucose. So we are discussing some properties of D-glucose. So let us see. Now, we know that glucose has an aldehyde group, which is this particular group you're talking about. So glucose has an aldehyde group. And we know that aldehydes give reaction with NH3. So we expect this glucose to give reaction because of this aldehyde group with a number of compounds, and some of them I'm going to write them down for you. So because of this aldehydic group, we expect glucose to give us some reactions, namely with NH3, also with NaHSO3, that is sodium bisulfate, and we expect it to also react with Schiff's reagent, because all of these properties are properties of aldehydic group. So we want to get a reaction out of D-glucose with all these reagents. But D-glucose, unlike normal aldehyde, will not show any reaction with all these because glucose exists in the cyclic structure. So it does not react. So we what we find out that it does not react with this, neither with this, nor with this. So it is not reacting with any of these weak reactants. So let us just write here to get this concept clear in our head that glucose, because of its cyclic structure, does not react with these weak reagent. Now, what happens is that now glucose is not reacting with them because it is a cyclic compound. But our normal aldehydes all give these reactions. So we see another reaction of glucose, and now we are reacting this particular glucose with, let us say, an HI. So now we are reacting our glucose with HI, that is hydrogen iodide. Now what happens is that when on prolonged heating with HI, it forms N-hexane. What is N-hexane? This particular structure, a straight chain structure of 6 carbons, is called N-hexane. So we have got 6 carbons. So we have got 6 carbons over here and a straight chain structure. So this is nothing but N-hexane. So D-glucose on reaction with HI is giving us N-hexane, suggesting that all the 6 carbon atoms are linked in a straight chain in D-glucose. So this is a confirmation to us that D-glucose has all the 6 carbons attached in a straight chain. As you can see here, 1, 2, 3, 5, and 6. So we have 6 carbons attached in a straight chain, which is proved by the fact that on reaction with hydrogen iodide, that is HI, it gives us N-hexane. Now, moving on to the next reaction that it shows. So now, glucose is reacting with CH3, CH3, CO, Cl. Now, what is this? This is nothing but acetyl chloride, and we know that acetyl chloride on reaction with alcohols tell us the amount of OH present. How is that? So if we have, say, an alcohol, suppose we have an ROH group, whenever it reacts with acetyl chloride, that is CH3COCl, this gives us CH3COOR. So it is removing this Cl from this particular area and giving us HCl. So now we can clearly see that it is the number of OH group present in an alcohol will be the number of acetyl chloride consumed. Okay. So when we react this D-glucose with this particular acetyl chloride, what happens is we require 5 moles of this acetyl chloride. This is what we observe. So when we were reacting, we observed that we required 5 moles of this to turn this into the product. And what was the product? The product looks something like this. So it was CH with a CHO group at the top, of course, and this CH, the OH, all the OH groups were removed, namely these OH groups were removed, and in place OH groups, we had the placement of O C double bond O CH3. The Cl was removed as was done in this previous example that I showed you. So these were removed and the placement of C double bond O CH3 took place. Four identical carbons at this place. So we get 4 here, and then the last one is also CH2 O C double bond O CH3. So now we can see that it removed all the OH, the 5 OH from the respective places, and it put O C double bond O CH3, that is in all these places, and we can see that since 5 moles of CH3 COCl, that is acetyl chloride, reacted with this, so we can now infer that D-glucose in fact has 5 OH group, that is 5 alcohol groups attached to it. So these all reactions we can see.